This example will show how to use Comsol multiphysics to set up a simulation that represents the hydraulic head between two streams. This watershed in Wisconsin includes some fairly complicated geometries. These are the streams right here. But we notice that many of these streams are roughly parallel to neighboring streams. So we could take a region like this one, where we have a square area that is bounded on one side by a stream and on the other side by another stream. And we could use this area to represent many of the other subregions within this watershed. So if we take a look at this square area, we see that we would represent the streams by constant head boundary conditions along the bottom and the top, recharge distributed over this region, and hydraulic conductivity that characterizes the property of the aquifer. These sides here would be no flow. So we'll use this general configuration to set up the Comsol model. So here's the opening screen for a Comsol model. We want to set up a 2D model that uses the Darcys Law physics. And we're interested in a stationary simulation. So this is the layout. The first thing we'll do is to define the geometry. So we expand this, right-click, and we'll select rectangle. So we'll create a rectangle that's 1,000 meters by 1,000 meters. Click this button up here to display the rectangle. This will be the geometry of our problem. We won't use this selection. Here's the physics, so we can expand this. And if we select fluid and matrix properties, we see that the rectangle that we've included is already selected. This is the subdomain 1. And if we go down here, we need to enter the density of water, which is 1,000, and we'll use the viscosity of water, which is 0.001 Pascal seconds, 1 centipoise. And for this model, we are given the hydraulic conductivity, so the permeability model we'll use is hydraulic conductivity, so we'll make that selection. And we'll change the default to 1e to the minus 6, which is the hydraulic conductivity for this model. Now these are the default boundary conditions and initial conditions. The default boundary conditions are no flow around all sides, and the initial value is that the pressure is 0. So we don't need to change these, but we do need to include the boundary conditions that represent the streams. So we'll select this, select Darcys Law, right-click, and we get several settings here for possible boundary conditions. And right there is the one we want, hydraulic head. So we select that. We go over here to the settings window. And what we need to do is select the two boundaries that we want. The upper boundary here, we click there and we press this to select that boundary. It shows up there. It's the boundary number 3. We select this boundary, which is boundary number 2. You can see down here that the hydraulic head along both those boundaries is 0. Now to include recharge, we go back to Darcys Law, right-click. These entries here allow us to specify conditions over an entire subdomain. These are boundary conditions. So the mass source selection is what we want for recharge. We select that. We select this subdomain to apply the mass source over. So there's subdomain number 1. And the mass source is going to be calculated like this. We have 1 times 10 to the minus 9 meters per second is the volumetric flux for the recharge rate, but we need to multiply that by 1,000 kilograms per meter cubed and divide that by 10 meters in order to get the proper units for mass source. Okay, we also select mesh, and we'll just use the default mesh. So we can click this button to generate the mesh. There's the default. And to run the model, we select study, and this is a stationary study. We'll just use the default settings. So to run the model, we select study and we press this equal sign. Here is the result. This is a plot of the pressure over the subdomain, and we can see this is an area of high pressure, 1.2 times 10 to the 5th pascals, and areas of low pressure where the streams are. And we want to plot this as the hydraulic head. So we expand it, and we click here, and this shows us the expression that's being plotted. P stands for pressure, and to plot another quantity, we select this button and go down to Darcys Law, hydraulic head, and now we have dl.h. That dl stands for Darcys Law, right there, and the capital H is hydraulic head. So we make that selection, and then we press this button here to plot. The distribution of hydraulic head is the same as the distribution of pressure for this particular problem, but we see now the units are changed. This is units of meters, which are shown right here. Now, in the previous example, we saw that this model also can be configured to show flow lines. So to do that, we go back to here and right-click, arrow surface. This will show us flow vectors distributed over the region. The x component and y component of the vectors are given here, and we plot it by selecting that button. These are the flow vectors. We are also interested in seeing a plot of the hydraulic head along a profile like this. So to do that, we go here to Data Sets and expand it. We right-click, and what we need to do is to define a line over which the cross-section will be taken. So we select Cut Line 2D, and we want a line at x equals 200, y equals 0, to x equals 200, y equals 1000. If we click this button here, we see the path that this line takes, like so. Now, to plot the cross-section along this line, we go back to Results, right-click, and select 1D Plot Group. This is the 1D plot group, and to plot something using these axes, we right-click again and select Line Graph, and to select the trajectory that we've just defined, we come down here and see Cut Line 2D, which is the name of the data set that we just defined. Select that, and we want to plot the hydraulic head along this line. So this allows us to select what is going to be plotted in this graph. So we left-click there and go down to Darcys Law, go to hydraulic head, and select hydraulic head. Now we can plot that by pressing that button there, and there's the hydraulic head along this line that we've defined.